Okay, in section 5.4, we are reviewing what you learned in Algebra 1 concerning factoring. And this is going to be a very important skill. The ability to factor is going to be very important for lessons that are going to come up later on in Chapter 5 and from time to time throughout the rest of the course. So let me go through some examples with you. The first few problems of your homework will involve the idea of finding a GCF, a greatest common factor, and then we're going to use that greatest common factor, if it exists, to factor the expression. So just keep in mind that factoring is another way, it's another way of representing an expression like this using two or more terms being multiplied together. So factoring, you can associate the word multiplying or multiplication. How can we rewrite this using the multiplication of two or more terms? So to begin with, the instructions say to find the GCF of each expression. GCF means the greatest common factor, the largest term that will divide into both 3a squared and 9. And that would be, hopefully you can see that that would be the number 3. Now GCF can be a number, it could be a variable, it could be a combination of number and variable. In this case, since 9 does not contain the variable a, I can't include a as part of my GCF. Okay, now factoring. Well, again, we're going to show this as two terms being multiplied together. 3 being the GCF being multiplied times some quantity. And the way I get the terms that go inside the parentheses is I divide the GCF into each of these two terms. So 3a squared divided by 3 is a squared, and of course 9 divided by 3 is 3. All right, so the GCF is 3, and the factored expression is 3 times the quantity a squared plus 3. All right, let's move on and take on a few more of these. Number 3, hopefully you can see that the GCF is going to be x. And now let's show the factoring. X, the GCF, would be multiplied by the expression. If you divide x into x squared, that's x. And if you divide x into 2x, that's 2. So you can always check your factoring with multiplication. Can I use the distributive property in this case and end up with the original expression? And the answer here is yes. All right, number 5. What is the GCF? Well, the GCF would be 7y. 7 goes into both 14 and 7, and they both contain y, and y is the lowest value or degree, y to the first. And so 7y is my GCF, and then showing the factoring, I will do 7y times the quantity 2y plus 1. Okay, I just divided 7y into the GCF into both of these terms. All right, now a little further down there's a block of problems that are going to require factoring. And I would just say this, it's very important that no matter what kind of factoring you end up doing, this should always be your first look. This should always be the first thing you consider. Ask yourself the question, is there a GCF? Now for number 7, there is no GCF, and we don't consider 1 a greatest common factor because dividing by 1 doesn't change anything. It doesn't change the look of this. It just gives me this again. So I can't rewrite this expression using multiplication times 1. That's not rewriting it. Okay, so I'm going to try rewriting it in this way. I'm going to rewrite it using two linear binomials being multiplied together. Remember, factoring means multiplication. Okay, linear again, remember linear means it's got to be x to the first power. Each of these have to be linear binomials, so each of them are going to have x to the first as part of their expression. Binomial means two terms. So the way I'm going to get the other parts of the binomial is I'm going to look at this last number, 2, and just think about all of the factors of 2. Well, there's only one pair of numbers that are factors of 2, so it makes this problem pretty easy. I'm looking for the factors of 2 that also add up to 3. Well, these two factors of 2 also add up to 3. So my final answer in factored form will be positive 2, positive 1. Now you could have also switched places with these. Multiplication is commutative, so either way you could have done it either way. Same answer. All right, and the way you could check yourself is by using FOIL. These are two binomials multiplied together, so I won't take the time to do it, but obviously if we use the FOIL method, we're going to get this result. Okay, so again, using multiplication of two factors to represent this trinomial in a different way, or that's what factoring is all about. Okay, number 9, I'm going to look for a GCF as just a standard practice, but there isn't one. Okay, well now I'm going to focus on the last number, 10. I'm just going to make a list of all the factors of 10. Okay, positive 10. I could do 10 times 1, I could do negative 10 times negative 1, I could do 5 times 2, I could do negative 5 times negative 2. I believe that captures all the factors of 10, but I need the combination of factors of 10 that add up to positive 7. And the only pair of numbers, factors of 10 that does that, are these two, positive 5, positive 2. So that gets me to my factoring, x plus 5, x plus 2. And again, you could have switched the 2 and the 5, and that would have been okay. Number 11, GCF, yes. 2 divides into 2, 16, and 36. It's the largest number that divides into all three. Okay, and so now let's take a look. Looking at the factors of 18, so once again, if you have to, just make a list. And I'm looking for the combination of factors of 18 that add up to positive 8. Okay, well, so far I haven't found any of these that add up to positive 8. All right, those don't add up to positive 8, and I think I've gotten all of the factors of 18. And so I can't factor this as two linear binomials multiplied together. I factored out a GCF, and that's as far as I can go. So that is my factored answer. Okay. Number 19, looking for a GCF first, always, but doesn't exist. Okay. So now I'm going to focus on the factors of negative 14. I could get negative 14 by doing this or this, but neither one of these added together would produce negative 5. These two factors added together would be negative 13. These would be positive 13, so I need to keep going. What about 7 times negative 2 or negative 7 times positive 2? Well, I think I've found the winner, because not only do these multiply to give me negative 14, but if I added these together, I would get negative 5. So my answer as two linear binomials would be x minus 7, and then x plus the 2 is positive. Okay, number 23, same routine, GCF, no. Okay, now I'm going to look at the factors of negative 75. Okay? All of these combinations of numbers multiplied together equal negative 75. But the trick is to find the combination that would also add to give me positive 10. And so far, I haven't found that. Okay? For example, if I add these two factors together, that would be positive 22. This would be negative 22. Obviously, I got negative 74, positive 74, so I got to keep looking. Okay, well, what about 15 times negative 5? That equals negative 75, and then if I were to add these together, 15 plus negative 5, that equals 10. So I found the combination. And so my factoring is x plus 15. The 15 is positive, and x minus 5. 5 is negative. And yeah, I can make sure I'm right. Just use the FOIL method, and you should get this. Okay, now we come to problems where the quadratic coefficient, if you notice up until this point, the quadratic coefficient, the number in front of the variable squared, was just 1. And that makes our factoring really pretty easy. But what about when the coefficient for the quadratic term is greater than 1? When this happens, and only when this happens, the only time I want you to use this particular method is when this quadratic coefficient is greater than 1. That's going to utilize what we're going to term as the box method. It's pretty easy. If you practice it enough, it's really not too bad, and I've listed the 4 steps of the box method. The first one is pretty simple. Just take the first term and the last term and put them across from each other diagonally. Okay? Step 2, I just want you to multiply those two terms together. And you can use a calculator if the numbers get kind of big. So if you put those two numbers together with multiplication, you get 130r squared. Okay? Step 3. Probably the most challenging step of all is right here. Don't give up on it because of this being a little bit of a challenge. You can do this. I need the factors of 130r squared, two numbers that multiply together to give me this, and those same two numbers when added together would give me the middle of this expression, positive 23r. And I came up with these. The factors of 130r squared would be 13r times 10r. And if I add those same two factors, I would get 23r. So those two factors are going to be placed in the other two squares. And it doesn't matter where. You could have switched places with these, and you would have still come up in the end with the correct answer. Okay, we're down to our final step. I've called it GCFs. I've made blanks here. You're going to find the GCF of both rows. So for example, the GCF of 5r squared and 13r is just r. Okay, drop down to this row. The GCF for 10r and 26 is 2. Now, do the GCF of these two columns, 5r squared and 10r. That GCF would be 5r. And for this column, the GCF would be 13. So what happens is these numbers, variable and numbers, represent our binomial answers, our binomial factors. So r plus 2, and the order really doesn't matter, 5r plus 13. So if you did a quick FOIL check, you should see that when you do FOIL for these, multiplying these two binomials together, you will get this. All right, that is the box method in action. So let's try another one. Okay, looking for a GCF always, but I don't see one. So now I notice that the quadratic coefficient is bigger than 1, so I'm going to go straight to the box method. So you need to show this box method only for those trinomials where the quadratic coefficient is greater than 1. So to begin with, we're going to put the first and the last terms across from each other diagonally. One thing I do know about the answer, what the factoring is going to look like, since we have a minus sign preceding a plus sign, you probably learned this in Algebra 1, that tells me that when I'm done, both of these signs are going to be negative. Okay? Because of that, I'm not going to worry about signs in the box method. I just think that makes it a little more confusing. We already know what the signs are going to be in the answer, so let's just put all positive numbers in here in the box. Okay. Okay, so I've done step 1, which is first and last terms. All right, that's step 1. Step 2 is multiply those two numbers together. 2x squared times 36 is 72x squared. Okay? All right, step 3, the most challenging part of this. I need the factors of 72x squared that add up to negative, or in this case, since we've already dealt with the signs, the factors of 72x squared that add up to 27x. And we could go through a whole list, but I'm just going to go right to it. If we did 14x times 3x, that would equal 72x squared. And if we took those same two numbers and added them together, they would equal 27x. So I'm going to put those two terms, and again, it doesn't matter which order, you could switch these. And now find your 4 GCFs, and you will be done. So the GCF of this top row is 2x. The bottom two numbers, the row, would be 3. All right, the GCF of this first column is x, and then for this second column, that would be 12. So my factored answer, and again, the order really doesn't matter. You can change places with these binomials. X minus 12, 2x minus 3. Do a quick little FOIL check. If you use FOIL, does it come back to the original problem? And it looks like it does. Okay. We have some special cases, and just want to review these special cases. For example, for number 43, we're supposed to factor. So again, I always just drill this in your brain. Is there a GCF? There is not. There's only two terms. This is a binomial, and we're subtracting. And so this special case is called the difference, subtraction, the difference between two squares, two perfect squares. Each of these terms have a perfect square root, in other words. So we have a special, really an easy way, if you can recognize that they are two perfect squares being subtracted, then it's pretty easy to factor. You just put the square roots, really you write the square roots twice. We're going to have two linear binomials multiplied together. One of your groups will have plus and the other minus. Doesn't matter which, you could switch the plus and minus. So the difference between two squares is a pretty simple way to factor. That would be the factoring for number 43. Just threw this one in as another example. Notice two perfect square terms. Both of these have perfect square roots. And so the factoring looks like this. The square root of 9x squared is 3x. The square root of 16 is 4. I'll make one of the groups plus and the other one minus, and we are done. Threw this one out just to warn you that we do not have a special way to factor the sum of two perfect squares. Okay, these are perfect square roots, but without factoring out a GCF, I really can't factor this anymore. This would be considered prime. So I don't want you to think that you can factor the sum of two perfect squares the way you do the difference. The special case only applies to the difference between two squares, not the sum. Okay? All right, I think I've given you enough. I hope I showed you enough of the box method, and go back and just review this. It's really not very tough. Make sure you get these 4 steps, follow them to the letter, and I think you'll be able to do these problems without any trouble. If you have any questions, let me know.